Good afternoon. So the motivation for this talk are some tricky requirements I had in a website I recently worked in. This website was built in Ruby on Rails. I am a Ruby on Rails freelancer, but although there's going to be some little details about the implementation of the interpreter, the Ruby interpreter, the majority of the talk is not dependent on Ruby, all right? OK, so this is a website for online betting we built from scratch. And the thing is, in betting, when you bet some money to some ratio, and if your bet is correct, then you are going to win some money, OK? Those are the numbers you see there, the stake, odds, and profit in jargon, OK? So you bet some stake, and if you win, you get some profit. And if you lose, you're going to lose your stake, which is your risk, all right? OK. The first big requirement we had up front is the system has to be a zero-sum system. So players bet against players, and so they are not playing against the website. They are playing between each other, and the website has a monthly fee or something that allows you to bet. Okay? So players bet against players, and the website should not need to put any money into the system. You know, everything has to be perfectly balanced. They also wanted to have a calculator where these three figures could be, any of them could be edited. So if you edit the risk, you may, dynamically be changing how much are you going to win, Otherwise, you could edit, I would like to win this much. How much should I risk? You could edit any of the three quantities. And I soon saw that the requirements couldn't be fulfilled. In this case, the problem is that in jargon, the backer is the person that makes the bet, and the liar is the person that sees that bet. So I am betting that Football Club Barcelona is going to win something, and then there's another guy that says, OK, I bet against you. So that's the other one. So the thing is, if you have the freedom to edit any of the three quantities, since in some direction you have a multiplication, but in the other direction you have a division, you do not need to understand these formulas. It's not necessary, but just believe me. You have a multiplication in one side, and on the other side, the other guy sees a division for the same thing. So what happens? If this guy wants to risk, the liar wants to risk 5,025 cents, is going to cover the bet. You see that this 200 and something is the same number we had in the first line, all right? But he can risk a cent less and still cover the bet. He can do that if he, tweaks a little bit the numbers, because the division is that one with 2 cents. So if he chooses the second option, the system is missing a 1 cent. And it still gets worse, because not only one guy can bet against another guy, but if you put 200 euros, you can have one guy seeing 5 euros of that, the other guy seeing 4 and 32, or whatever. All right? So the bet can be covered by several people. The problem here, I'm not going to explain also the details, but the problem here, if you have made an invoice anytime, at least in my country, in invoices, if you have several lines and you need to apply a tax, first you add the lines that gets you a number, and then you apply the tax to the number, all right? You cannot do that line by line. Well, if you do that line by line, in general, the result is going to be different. And the problem here, some people call this rounding off error. I don't call it rounding off error. I call it a business problem, because the problem here is that the multiplication we are symbolizing here is not really the multiplication of the numbers. It's multiplication of money. And the multiplication of money always gets you 2 cents. So it's a different operation with different properties. So it's not a matter, if you were like with a notebook and pencil, serving requests in the server, you yourself, you couldn't solve this. It's a business problem, it's ill-defined. All right? So this project needed arbitrary precision to be able to represent numbers not only with cents, but with whatever you need, and also exact arithmetic. We need exact addition, we need exact multiplication, and exact division. All right? Arbitrary precision, well, the first solution to this problem is proposed to the stakeholders that they change the requirements. This was actually the first proposal. Guys, this cannot be implemented. There's no period. It cannot be implemented. It would be a good idea to change the requirements. They didn't want to, especially the requirement of being able to match a bet among several people. So that was the situation, and we solved it. And I like to share with you in this presentation, the path we took to solve this and what was the final solution. So with this excuse, we are going to see a few numerical types with some details related to Ruby, but in general, most of them apply to any programming language. The first type is the forbidden float, and I put forbidden because floats, I don't know. Especially if you're working with money, you all know that you shouldn't be touching a float at all. But let's explore why is that the case, why floats are generally not a good idea. So probably you all know floats that have these weird properties, like we would expect that to be true, but it's false. And you know that a decimal number is written in a certain base, and the meaning of those, the meaning of that representation is this thing with the powers, in this case of 10. All right, you probably know that a float, behind the scenes is represented this way. We have here a series of bits. We have a sign. We have a range of bits that represent an exponent, and a range of bits that represents a mantissa. That's a standard, and that's a topic for a whole talk. So only refresh this thing which you probably already know. All right, and you probably know that this is for the most part, this is the formula that gives you the number that is represented in that float. So S the sign, M the mantissa, and E the exponent. Here, the important part is the 2. As you know, numbers in computers are represented, at least these kind of numbers, in base 2. Okay? So why is this false? Let's have a look at how those numbers actually represented in the computer. So what we are seeing here is each of those numbers, so 0, 45, 0, 44, and 0, 0, 1. This is the dump of the actual representation in the float. I wrote a C program to print this information. And you see, there's a lot of zeros of ones, so the laser is not seen, right? Okay, so we have 3 blocks, all right? in the 3 blocks, we have first the number, then the sign bit, then the exponent, which is the shorter series of zeros and ones, and then the long one is the mantissa, okay? So that's for each of the numbers. What we see here is that the mantissas are nothing but simple. There's a series of zeros or ones here. And yeah, so that finite number is not the number we entered as a literal, in our source code. And together with the literal, we have the fraction. You see those big fractions? That fraction is the, if you take the float and apply the formula, it doesn't give you that 0.44. It gives you that fraction, that big fraction. So what's happening behind the scenes that the literals you have in the source code are not, the numbers that the computer is representing. But why? Why so many binary digits? I mean, the number initially was like super simple. It was just, I don't know, very short. But there's a lot of ones and zeros here. Why that? So let's recall something you probably know even from high school, which is that some fractions have a finite decimal expansion, like the first one, okay? You get a finite decimal, the fractional part is finite, or either you get an infinite representation, but with a repeating part, all right, with a period. You remember that, all right? There's the only two possibilities there are for fractions. OK, we know that. So the key point here is that while this is true for all fractions, for all rational numbers, whether the representation is finite or is infinite depends on the base. That depends on the base. So a number, a number is an abstract entity, all right? So the number 2 is an abstract entity that we can represent with a numeral, with a Roman numeral. The representation is another topic, all right? So the representation using different bases have different properties. In particular, whether it's finite or not depends on the base. And how depends on the base? It depends precisely this way. So if you take the fraction in lowest terms, you get a finite representation if and only if the denominator q divides some power of the base. That's the rule. If that holds, you get a finite representation in that base. Otherwise, it's infinite repeating. OK? Depends on the base. In particular, if we are talking base 2, you get only finite representations if the denominator is a power of 2. All right? So that's the point. And if you apply this corollary, you are going to see that there are only four numbers with whose sense, four numbers less than 1, whose sense can be represented precisely with floats. Only 4. The rest, you are fucked. OK, so floats, absolutely forbidden. There was a rule in the project that said, no way we are going to touch a float. So even rounding to get, I don't know, a string represented, no, nothing. You cannot touch a float at all. Integers is a common way to represent money. In Ruby, we have arbitrary precision integers. So for instance, this is the factorial of 100. All right? It's just there. Okay? You do not have the limit that some other languages have with integers. All right. And there's a distinction between what are called fixed nums, which means that they are more or less like an immediate value, all right? And big nums that means there's an object representing the, more digits or whatever. Big nums are the big ones, need more stuff to be able to represent the big number. And fixed nums, you can think about fixed nums as, closer to the machine, all right? I believe, if I'm not mistaken, Common Lisp has also this terminology, fixed nums and big nums. All right, and this is an interesting bit about Ruby. So in Ruby, normally you have references to objects, all right? So when you get, in a variable, you store a reference to an object. It's something opaque, but it's a reference. It's like a pointer, let's say. All right. Indeed, behind the scene, it is a pointer. And Ruby uses tagged pointers to represent fixed nums. So, in a fixed num, instead of a pointer, Ruby stores the number, except some bits, all right? So Ruby takes advantage of the fact that the pointer cannot end in 1 or something like that, and it puts a mask. It shifts the number, puts a mask, so you don't have the whole range, the whole, native integer range. But you maybe lose a bit or 2 or whatever, but you are able to store the integer in the same pointer, and that way, that's going to be much more efficient. You do not need to go fetch an object, interpret the object, whatever. You have the integer right there, all right? So there's a shift, and then if you want to read the integer, there's a shift in the other direction, and you get the number. So it's not like for free. You still need to do a shift, all right? But it's going to be cheaper than other alternatives. And this is the function that computes the successor of an integer, just to see how it works. So basically, the successor function tries to add 1 to the number. If that number plus 1 fits into the smaller range of those integers, it's going to leave it like that, all right? Otherwise, it promotes the integer to a big num, okay? Okay, the source code here, but we are not going to do the walkthrough. It just was, for depicting the way it works. So it goes to big num as needed. And this is the way big nums are represented in Ruby. And as far as I know, this is a very common way to represent arbitrary precision integers, which is that you have an array of digits, and here the base is huge. So basically, if you have an array of ints, every int represents a digit, all right? A digit which is going to be really big, and we do not have, a numeral to write that digit with, with just one trace or something. But it's going to be conceptually a digit in a very huge base, all right? So to represent a big number, maybe you only need 2 ints, okay? All right, so you have an array of big digits in a big base, and then, because this is C, you store the length of the array. And then there's a lot of interesting things here, because the way you choose the base, the way you implement the arithmetics, because you can multiply, you can do things with this stuff. It's a whole topic, and there's this really nice C library, call it libtommath, which is written in very, very clear C code, whose purpose is precisely to discuss how to implement. There's a very, very well-written user manual that explains the trade-offs, the way things are chosen, and the algorithms and everything. It's a very interesting topic if you want to explore a little bit more of this. The pros of integers are, first, they are fast. They are exact. So you know that if you are representing cents in integers, you are done. If you are multiplying cents, well, you need to either keep track of the rest of the fractional part if you want arbitrary precision, or either do explicit rounding. So if you are in a situation, our situation was unusual because we need arbitrary precision, but normally you do not need that. You only need cents, and that's it. And in that situation, something I like about integers is that it forces you to be very explicit about in which points in the system you need to do a rounding, because you have to do it manually. All right? So if you multiply, I don't know, a price by some fractional unit, and you get more a fractional part that has millicents, you have to make a conscious decision. Okay, I need here to round, and I am going to round using this rule. Okay, so it gets you discipline working with this stuff, which is very important. When you are working with money, I don't know, there's little margin for errors. All right. There are some cons, which in my mind are minor. First, display. You have an integer with cents, all right? Well, you need to put a comma there if you want to display that as cents. No big deal. Multiplication needs to be done by hand, okay? You need to multiply and round or whatever. Maybe you can use a library to simplify that. And, well, if you need division, yeah, all right, so we are still in a square one, okay? Division is not going to fly. Okay. Another interesting data type are big decimal. Big decimal, it's also present in Java and other languages, allows you to represent numbers with fractional part arbitrarily large and without a change in base. So that's the point. So for instance, I am using here Ruby notation, but it's going to be the same in Java or whatever. In this case, we instantiate a big decimal with the numbers that didn't work before, and now the comparison is true. It holds. An important point here, just in passing. Note that we are instantiating big decimals using strings, all right? That's super important. I've seen people instantiating big decimals using float literals. And you are fucked, again, if you get a float literal in the source code, that float literal is going to be converted, to that thing that is not exactly what you mean, and then it doesn't matter if you construct a big decimal. You are going to construct a big decimal of another number, all right? So we are using strings here because the string is clearly what we want the big decimal to represent, and it's going to work, okay? That's going to be, we are not losing any information here. Okay. How is represented internally a big decimal? So it's very common sense. We have in floats we have a mantissa, which is it has a fixed amount of space. In big decimals we have as mantissa an arbitrary precision integer, an integer that can be as big as you want, as big as you have memory in the system, or whatever physical constraint, but not limited in the sense of the same limitation a float has. All right, you have an arbitrary precision integer here. Then, and this is the most important property of big decimal in practice, which is that this mantissa is using a power of 10 as base, power of 10. And that's super important, because that's what guarantees, according to the results we've seen before, that what guarantees that if you have a finite decimal fraction using base 10, it's going also to be finally representable in a big decimal. Okay? Here we are using a base of 10, and the property we saw, okay, if the representation is finite in 10, it's going to be finite in a power of 10, and vice versa. All right? So that's the key point. If I can write the number using 4 decimal, fractional part with 4 places, that's going to be exactly representable in big decimal. If we had something in base 2, then we would lose, information there. But if you work with base 10, which is the way we normally work, base 10 and you need, arbitrary precision, you are going to accomplish that with big decimal thanks to choosing this base, a base which is a power of 10. It's not 10, but a power of 10, again, to save space, because maybe the array, it's an array of integers, and if you get a big power of 10, every one of the places can be interpreted like a digit in this huge base, and that allows you to represent big numbers in a very compact way. Okay. Then you have the exponent and the sign and some internal flags, which are used by Ruby. All right, so with big decimals, we have something solved, which is having arbitrary precision. If we are working with money, how do we introduce arbitrary precision in the system? Because money is, at least if we work with dollars or cents or euros or these kind of currencies, we are talking about cents. So there's no millicents, that has no meaning. And we could exploit a hack here, which is that actually in the website you get credits to bet from money. So there's a payment gateway, and say, I'm going to transfer from my account, I don't know, 300 euros, and that's one-to-one to credit. All right? So you have money, a payment gateway, and you say, I want to put 300 credits in the system. So credit is something that we define, and that's what we exploit. So our suggestion was, let's redefine credit. So money, because the world works that way, is fixed. You have to work with cents. But credit is up to us. So let's define credit as something that has arbitrary precision. Then, if you have millicents in credit, you are not going to be able to transfer that to real money. But the stakeholders had no problem with that. All right? Okay. So arbitrary precision, good, but not enough. Because since we are working in base 10, if you want to divide 1 divided by 3, that's not finite. That's not finite. That's a repeating decimal, number. So that's not a solution, because we need to be able to divide exactly. Okay? So big decimal is arbitrary precision as long as your number has a finite representation. Otherwise, it's not magical. It's not going, because it works the way it works. It needs a finite mantissa. It cannot represent this thing. All right? So arbitrary precision, good, and division, no. So rational numbers. Rational numbers is the fancy way to say a fraction. A fraction, we all know fractions. A fraction is an integer divided by another integer, which is not 0. All right? That's a fraction. And the fancy name, rational number. Okay? Rational numbers come with Ruby in the standard library. And the representation is it's very simple. So this struct basic is something internal to the interpreter, doesn't matter. But you see, we had before mantisas and arbitrary precision stuff, I don't know, you know. And here we have a numerator and a denominator, and that's it, okay? And they are arbitrary precision integers, all right? So rational numbers, if you remember from high school, if you can add two fractions, if you add two fractions, you get a fraction. If you subtract two fractions, you get a fraction. If you multiply two fractions, you get a fraction. And important, if you divide two fractions, you get a fraction. All right? So that was our solution, work with rationals. All the system is based in rationals. The pros are these ones. We can, you know, the requirements are good, and that's a big pro, all right? It's arithmetic, including division, okay? And the second property is kind of ambiguous, but what I mean there is that the representation of a rational is so simple that you kind of, I don't know, you kind of going to be confident that across technologies are going to work, because the calculator is written in JavaScript, the application is written in Ruby, and then we have Postgres as a storage. So I don't know, we have to divide, across these technologies, and okay, with other representations, you can find edge cases. But rationals are so simple and the rules are so clear, because the arithmetic is super clear, that you can more or less be confident that across technologies they are going to work. I wrote a CoffeeScript class, very simple CoffeeScript class to represent rationals in JavaScript, and Ruby has rationals, and I am going to tell you how did we solve the Postgres thing. Cons, display. This is an important cons, and it's something that when we said, okay, rationals solve the problem of this website, but you cannot tell a player that his credit is, I don't know, 2/5. You cannot say that, all right? So we said, all right, so we are going to be ambiguous in the sense that we are going to say somewhere that we work with arbitrary precision internally, but the user doesn't care about that, all right? So we cannot also hide this precision from the user, because if we tell him that his credit is this number and it's a little bit more, and then you get a subtraction or something and it doesn't, it doesn't match, it's going to be suspicious, all right? From the user perspective, you're going to see that it doesn't match. So the decision was, all right, we are going to work mostly with cents in the interface, but if there's more digits than the cents, we are going to put a plus sign. So maybe your credit says you have, I don't know, 5.32 plus. What's plus? Doesn't matter. It's, we have more precision, but we are not going to show it to you, because the website you have still, the mindset is cents. So the technological solution is this, but still you cannot promote that to the interface. All right. So the mindset of if you see the whole UI, everything is cents still, with some pluses here and there, but they are very subtle. All right. So it's not an important cost in terms of user experience. They are kind of slow, of course. It's not the same thing multiplying or doing arithmetic with fractions that doing them with integers, all right? But in our case, it doesn't matter, because the operations we have to do are very trivial, and we do not need, I don't know, to do like number crunching using fractions, you know? So in our case, it doesn't matter. And it doesn't matter less if it solves the problem, of course, because other types are faster, but doesn't solve the problem, right? So the other one is persistence. OK, we need this in the database. What do we do? One solution, of course, is to represent things using 2 integers, all right? But that could be suboptimal. We would do it if needed, but it would be suboptimal because then you do not have the number, you know, easily in the database. You have 2 columns with integers. But what if you want to compute, I don't know, how much this guy has bet? You know, I don't know, this game, which is the amount of money bet so far in this game. You need to do some stuff, you know, at the SQL level. What do we do? So fortunately, there's a Postgres extension that it's a bridge to a GNU C library that implements arbitrary precision, and in particular implements rationals. So that was like, wow, this amazing. You have solved here like a big problem we would have otherwise. Because this adds to Postgres rational data type, and also, if I remember correctly, an arbitrary precision integer data type. And the cool thing there is that you have, from the point of view of Postgres, that's another data type. So you have the entire SQL. You can compare, you can add, you can do whatever you want, all right? So amazing, amazing. We solved, luckily, we didn't have an issue in the database. In addition to that, it's plenty fast. I mean, if you want to add, I don't know, 1 million rows, it's wow, it's like that, all right? Very fast. So that was the story of this website, and thank you very much.